Hi there and welcome to PhD at Living. This is a meter. Well, actually it's a piece of wood that says it's a meter long. But how do we know it's a meter? Was it calibrated against some other thing that said it was a meter long? And what about that thing? Does it ever end? Is there like a single meter that every other thing that says it's a meter long is calibrated against? And what about a kilogram? What about temperature? What about how long a second is? Well, I'm sure you've never wondered these things, but it turns out it's actually, oddly, pretty fascinating. And more fascinating, a number of these fundamental units of measurement were radically changed in 2019 in what the United States National Institute of Standards and Technology called, quote, a turning point of humanity, end quote. And most fascinating and selfish, I, a scientist who uses these units of measurements regularly, didn't even find out about it until 4 years after it happened. You guessed it, folks. It's another episode of me daring you to keep watching something this niche and ridiculous. Let's start with a wicked brief history of measurement. Why is an agreed-to system of measurement important in the first place? Well, without going too far into the weeds, trade is the answer. You can easily count integers like the number of fingers or goats in a field or something, but any more complicated than that and things get pretty dicey. You aren't going to count every grain of rice in a gigantic bag, for instance, so you need to account for that mass in some aggregate way. What about length? Well, we used to use the length of a forearm in fingers, or a cubit. This unit of measurement was referenced pretty frequently in the Old Testament or Torah, and people with technology of thousands of years ago had already figured out this need for a reference standard thing. Fast forward to 1585, and Flemish mathematician Simon Stevin proposes the use of a decimal-based system, that is, base power of 10. 10 millimeters equal a centimeter, 1,000 meters equals a kilometer. Compare that to the imperial system, where 12 inches equals 1 foot, 3 feet equal 1 yard, and 5,280 feet equal a mile. This base 10 system was popular, but didn't become universal until, of all things, the French Revolution. That's where the metric system we now know and love was developed, and it defined our units of length and mass. The meter was based on the size of the Earth, and the kilogram was based on the mass of water in 1 liter. We will get way more into the weeds on both of these, so just sit tight. Oh, also, one notes that the mass unit was based on a volume unit, and one wonders how accurate the liter was to make the kilogram accurate, but it's like 1795, so cut them some slack. The official start of the International Metric System was the Pitre Convention, aka the Treaty of the Meter, in 1875. 17 countries, including the United States, ratified to create the International Bureau of Weights and Measures, the BIPM, an intergovernmental agency under the auspices of the General Conference on Weights and Measures, the CGPM, and the supervision of the International Committee for Weights and Measures, the CIPM. No, you don't need to remember any of that, and I don't know why I'm talking like this. Yeah, I know all that's pretty confusing, so here's the gist. The General Conference is the body that does a lot of the major updates to what we now know as the SI System, or International System, or French Système International of measurement. It was officially established in 1948, various units were defined, and it was dubbed the SI System in 1960. Fast forward 58 years, and aside from a few nominal minor changes, the metric system looked pretty much the same as it did in 1875. But boy, that 2018 meeting was a doozy. A bunch of units got redefined, constants were made exact, and the BIPM concluded, quote, for the first time, a complete set of definitions is available that does not make reference to any artifact standards, material properties, or measurement descriptions, end quote. With that, the accuracy of any measurement or standard was limited only by the laws of physics holding true, and our technical capabilities to reflect them. Pretty rad, no? And here it is, folks, in all its glory, the improved International System of Units. Yes, the SI system is, at its heart, just 7 constants. 7 things with defined values of absolutely, positively no uncertainty whatsoever. All other measurements and units of measurement can be derived from these 7 things. The unperturbed ground state hyperfine transition frequency of cesium-133, 9 billion whatever hertz. The speed of light in vacuum, c 299 million whatever meters per second. The Planck constant h, 6.626 whatever times 10 to the minus 34 joule seconds. The elementary charge e, 1.6 whatever coulombs. The Boltzmann constant k, 1.38 whatever times 10 to the negative 23rd joules per Kelvin. The Avogadro constant, 6.022 whatever times 10 to the 23rd per mole. and the luminous efficacy of monochromatic radiation of frequency 540 times 10 to the 12 hertz, you guessed it, 683 lumens per watt. And that, my friends, is the SI system. You'll note these aren't particularly practical for figuring out how much the watermelon at the store weighs or how long the length of pipe you need at the hardware store is, so BIPM have done us all the favor of deriving our favorite base units from these constants. Hopefully these ones will look a bit more familiar to you. In order of quantity, time using the unit second, length using the meter, mass using the kilogram, not the gram, a lot of people get that wrong, electric current using the ampere, thermodynamic temperature using the Kelvin, amount of substance using the mole, and luminous intensity using the candela. Yeah, but how do you get from the Planck constant to the kilogram? And did anything actually change about temperature and time? And also, why in the hell does any of this matter? So glad you asked. Come on in. Let's start with the one that started it all, the meter. Historically, length has been defined by things that are readily available, but not very exact. The length of a foot, for instance, i.e. the foot, the length of a forearm, or the length of 3 barley corns stacked end to end. If you're watching this channel, you clearly recognize the need for something a bit more accurate, so in the midst of lopping off heads and creating a new form of government, the French Revolution created the meter in the 1790s. The meter was initially defined as 1/10,000,000th of the distance between the North Pole and the equator, naturally passing through Paris. In 1792, 2 French astronomers started surveying the distance between Dunkirk and Barcelona in order to prove out the meter. 7 years later, must have been some trip, they submitted their findings and the first international prototype of the meter was made from platinum. 2 years later, they realized the length was wrong by 0.2 millimeters because the scientific community had inaccurately measured the curvature of the Earth. Shame. No official change to the meter, however. Everything just became, 0.2 millimeters off of what it should have been. As the meter gained popularity, more countries started using it. That unfortunately introduced the opposite problem to that of antiquity. Instead of having inexact reference standards that were plentiful, lots of feet and forearms and barley corns in the world, we moved to having a single exact, for the time, reference standard, but there was only one of them and lived in a vault outside Paris. Problem being the practicality of a standard like that was not so good. Not to worry. The community just made copies of the thing, and then those copies could be used as calibrated substitutes for the genuine article. This was pretty much literally the purpose of the BIPM, the CGPM, and the CIPM. That is to say, demonstrate without a doubt the veracity of the meter and its copies for official standardized measurements. Hence, the Treaty of the Meter in 1875. As a result of the treaty, a new meter was fabricated. Wake up! Hi, welcome back. We're at the part where it gets good. The new meter, or international prototype of the meter, was made from 90% platinum and 10% iridium. The addition of the iridium greatly increased the hardness of the alloy, but didn't affect a lot of the platinum's otherwise very desirable characteristics, including extreme oxidation resistance, very high density, so your material artifact didn't have to be that big, and very good electrical, thermal, and magnetic properties. In theory, this meant your literal meter would be very resistant to change, which is a good thing if that literal object is defining length for the entire planet. A few other fun design features of the new meter included this thing. What's this? Well, torsional strain could change the length of the object during measurement. To minimize that, the new meter was constructed in this modified X shape called a Tresca section, in honor of its inventor, Henri Tresca. This provided maximum stiffness to the meter, and this section here in the middle would maintain the meter's length if it encountered any torsional bending during measurement. The meter being made of metals, the coefficient of thermal expansion would change the length of the object depending on the temperature. For that reason, all measurements of the meter would be taken at 0 degrees C. Incidentally, future advances in metallurgy resulted in alloys that had essentially 0 CTE whatsoever. These would have been great materials with which to make a new meter, but we'd discovered better ways to measure length by then, so they ultimately weren't used. The bending of the bar during support, obviously shown here in a very exaggerated way, was standardized to correspond to the airy points. That is, the way in which you'd support the meter where the ends of it would be exactly parallel to each other. Thus, for official measurements, the meter would be supported by 2 posts 1 centimeter in diameter placed exactly 571 millimeters apart. Finally, the meter was not an end standard, meaning the literal length of the thing was not 1 meter. Designed to prevent artificial invalidation if the ends got dinged, chipped, or eroded, there were markings on the inside of the meter that denoted the official meter length. And that's the way it stayed until 1960. Don't get me wrong, the community's ability to accurately measure length increased, but the BIPM and CPGM didn't move until those techniques had proved themselves out. Specifically, advances in interferometry significantly increased the resolution for the measurement of distance, and it had the added benefit of not needing a physical artifact in order to demonstrate it. Finally, in the 1940s, scientists discovered that Mercury 198 emitted an extremely reproducible wavelength of green light. The Mercury 198 came from bombarding stable gold 197 with neutrons to create gold 198 and induce beta decay. Count up a certain number of these Mercury 198 waves, granted the wavelength is in nanometers, so it would be a lot of them, and you have yourself a meter. NIST used that through about the 1950s, but CPGM ruled in 1960 that from that point on, Krypton 86 would be the standard for wavelength, and thus the meter. This lasted for about 20 years, when the new definition of the meter was based exclusively on the speed of light via this equation, c equals length over time. If you knew the speed of light very accurately and could very accurately measure how long that light traveled, then you'd have a very simple and very accurate way to define your length. Here's another one. C equals lambda nu, wavelength frequency. If you can very accurately get your wavelength and frequency of a given electromagnetic radiation, multiply them together and you very accurately get the speed of light. Turns out laser tech through the 1960s and 70s made this possible, and that led us to our current definition of C at 290 million whatever meters per second. The CPGM took that and redefined the meter in 1983 as the distance traveled by light in 1/290th of that of a second. In summary, the meter was changed from being defined by a physical object to being defined by the speed of light, which was now defined as an exact constant, that is to say the speed of light is that number to as many decimals as you need, and the second. In practice, the length of the meter stayed the same, so nothing really changed, but as a recurring theme of these units, scientists could now independently verify that unit of measurement without comparing it to, a chunk of metal in France. This is great and all, but it brings us a new problem. If the meter's defined by the second, how do we define the second? Turns out this is the perfect time to discuss, time. Aside from the mole, every SI base unit is derived at least in part by the second. This makes our definition of time probably the most important unit in all of science. Post-antiquity, the second had pretty much always been defined as a fraction of one rotation of the Earth, 1/86,400th to be exact. Until the resolution of our scientific instruments caught up with the irregularities of Earth's rotation, this worked great. However, at a certain point, we became better at reproducibly measuring the second than the Earth was at reproducibly delivering it. Hence, in 1960, the CGPM, remember part of the global BIPM, declared that a second would no longer be based on the Earth's rotation, but rather on Earth's orbit around the Sun. A second would now be 131,556,925.974 of a tropical year. Yeah, okay. This, unsurprisingly, only lasted a couple years before CGPM announced it wasn't accurate enough for current measurement techniques. Also, it was dumb. Clearly, something better was needed if the definition of the second was going to keep up with our ability to measure it. Let's go back in time. Pun a little bit intended. The first mechanical clocks in the 1300s were about as accurate as a sundial from ancient Rome, about 15 minutes a day. Fast forward to 1904 and you get NIST's first official time standard, the Riefler clock, that was accurate to about 3.5 seconds, not per day, per year. Another 25 years on top of that, and you get the short clock, which replaced the Riefler in 1929 and was accurate to about 1 second per year. As you can see, these things are very accurate, but they're not accurate enough for today's scientific measurements. Plus, temperature expands and contracts gears, a pendulum's oscillation varies on its altitude because of gravity, and friction is always present to literally slow things down. So, what to do? How do you find something that is accurate enough to define a second without being subject to all those nasty physical phenomena? Here's where it gets really interesting. As early as the 1870s, Maxwell and William Lord Kelvin Thomson proposed a natural clock based on atomic emission. Here are the premises. Number one, all atoms of a given element are identical, meaning that all emissions of a given excitation on a given element should also be identical and hopefully highly reproducible. Step two, frequency is expressed in terms of oscillations per second, or hertz. Number three, if you could reliably and accurately count the number of oscillations of a given emission from a given element, you'd have essentially a completely bulletproof way to measure and define the second based on a simple reciprocal of the measured frequency. There was, per usual, only one problem. We had absolutely no idea how to do it. Remember, this is the 1870s. The electron wouldn't be discovered for another 25 years, and the nucleus, the proton, and the neutron wouldn't be confirmed until well into the next century. It took until the late 1940s for an atomic clock to be demonstrated, and things only got better from there. Recall that all we need to do in an atomic clock is count oscillations. Electromagnetic radiation often comes in sine waves like this, with a lambda, a wavelength, that is the distance between the waves, and a frequency, a nu, that is the number of oscillations that pass in a given period of time. As long as you have something that can accurately count the ups and downs of the oscillations, in theory, you can split time into as many chunks as there are, well, oscillations. Now, any atom can do any emission like this, but to get the required accuracy for redefining the second, you need to find an atom that has an extremely reproducible and reliable emission that can be extremely reproducibly and reliably measured. For a super accurate measure of time, you would need a reliably accurate emission that had a narrow line width, no interference from other waves, a single isotope from your element, no interference from other isotopes, and preferably an easy electron environment, no interference from other electrons. As it turns out, the element cesium, and in particular the isotope cesium-133, checks all of these boxes beautifully. Namely, cesium-133 is the only stable isotope of cesium, and it has a single valence electron in the 6s orbital, so that's why it checks these two boxes well. Another cool thing cesium-133 has is an electron spin of +1.5 and a nuclear spin of 7/2. I don't know the quantum mechanics of this, but the specific pairing of those spins creates a magnetic environment that splits the standard atomic energy levels into sublevels. These sublevels are called hyperfine structures, and the movement of electrons within those hyperfine structures is called a hyperfine transition. In what is the simplest electron diagram I've ever drawn, here's what happens during cesium-133's hyperfine transition. You can see our single 6s1 electron sits at sublevel 3. Upon excitation, it moves to sublevel 4. When it comes back down, it releases energy at a defined, to be exact, frequency of 919,263,1770 Hertz. Again, this number is defined. It matches the old definition of the second, but it's way more accurate because it's not dependent on the Earth's rotation or orbit around the Sun. Hang on. Gonna need to hear that one again. Hey, no worries. This one took me a while to get to. The reason why we use cesium as opposed to some other element is that specific hyperfine transition emission on that specific element is so daggone reproducible. There's nothing special or fancy about the frequency or wavelength number, it's just some random transition in the microwave region. If we could find something that emitted light at a frequency of 1 Hertz, then every time the detector saw one oscillation of that light emission, that would be 1 second. What makes cesium special is really just the reproducibility with which that transition can be produced and subsequently measured. An atomic clock is really just a stream of cesium atoms that are vaporized and excited to emit that exact hyperfine transition. The detector of the clock is really just a counting apparatus, and once it gets to X number of emitted oscillations, 9,192,000,000 whatever, a second has elapsed. Restated, the atomic clock works by the detector counting the number of oscillations of that hyperfine transition of cesium, and when it gets to that number of the frequency in hertz of that cesium oscillation, a second has elapsed. It just counts. It's not a gear or a pendulum, but that specific radiation emission is so reproducible that it literally defines time for us. Recall that a really good clock from the 1920s wouldn't gain or lose a second while running continuously for about a year. Now this is the resolution that we're going to talk about the rest of the way because the numbers get pretty outrageous. How long would the clock need to run continuously before needing to be retuned within 1 second of accuracy? NIST's first cesium clock in the 1960s could run, theoretically, it's not a mechanical clock, for 3,000 years without losing 1 second of accuracy. 5 years later, that number was 10x. In 1975, the cesium Mark VI clock could run continuously for 400,000 years without losing a second. And in 1993, the cesium Mark VII clock at NIST could run continuously for 6 million years without losing or gaining 1 second. Remember that we're not talking about any imprecision in the cesium radiation emission. That frequency is never going to change. Rather, the precision we're talking about is the clock's ability to accurately count the number of those wave oscillations in defining what a second is. And that, my friends, is... But wait, there's more! In 2022, the CGPM voted to change the definition of the second again. There's a new technology called an optical clock that is accurate to within a second's time in, wait for it, 6 billion years. The cesium clock is based on a frequency in the microwave region. Optical clocks, as you may guess, are based on frequencies in the optical region. These frequencies are 10,000 times larger than those of the microwave region in the cesium clock, hence the accuracy with which the second can be measured is, in theory, also 10,000 times better. The actual implementation is a bit more complicated than that, but for the purpose of this video, that's all we'll go into, with the encouragement to check out the link in the description below to NIST's Mercury clock. Alright, finally, in summary, the second used to be defined as the fraction of time it took for Earth to rotate around its axis or orbit the Sun. Those astronomical values, while accurate, were not accurate enough for advanced technical measurement in the 20th century. For that reason, time and the second are now defined as how long it takes for 9 billion and change oscillations of a specific hyperfine transition in the cesium-133 atom take to occur. Now time for our next unit. Guess what's coming up? Let's switch gears a bit and move to temperature. We've already talked about it a bit in regard to absolute zero, and I'll summarize to say that temperature has historically been measured in relation to something being hotter than or colder than something else. This led to our relative temperature scales using degrees of either Celsius or Fahrenheit. William Thomson, aka Lord Kelvin, was the first one to introduce an absolute temperature scale, meaning no negative numbers, and 0 Kelvin meant no temperature. Or, in the awesome parlance of that time period, infinite cold. Water being a great reference standard with phase transitions that happen at temperatures achievable at home, scientists used our elixir of life to define the Kelvin, the unit, not the scale, for over 100 years. As anybody who's cooked pasta at altitude knows, however, the temperature at which those phase transitions occur is dependent on ambient atmosphere. For that reason, the scientific community needed a way to define temperature that wasn't dependent on pressure. Enter the triple point. Here's water's phase diagram. For much more on this, check out my ice skating video. For today's discussion, however, suffice to say there's a temperature-pressure combination at which all three phases of water, gas, liquid, and solid, ignoring for now the supercritical fluid cheat code phase, can exist at the same time. This combination is called the triple point, and it's how the Kelvin was defined for a long time. To make it easy for those of us using the metric system, 1 Kelvin was defined to be the same as 1 degree C. The temperature at which the triple point of water occurred was defined as 0.01 degrees C, which converted to kelvins is 273.16, which means 1 Kelvin was, 273.16 of that. Which is great and all and works relatively well until you realize you need extremely pure water to achieve that triple point at the correct temperature. Any little bit of impurity messes up the measurement. Okay, so just distill it. Right you are. What about isotopes? You telling me it makes that much of a difference? Bro, we're talking 250 microkelvins, man. That dog's not gonna hunt. I can't believe you. I know, right? Hydrogen's main isotope is, of course, H1 at greater than 99.9% abundance, but we also need to account for the deuterium, H2, at 0.0145%, and tritium, H3, which is only at trace amounts and is radioactive with a half-life of 12 years or so, but is measurable and needs to be if you want that temperature to be exact. Oxygen, on the other hand, has 4 isotopes, naturally occurring, O15, which is radioactive and trace, but again we need to measure, O16, the one everybody thinks of, and O17 and 18 at 0.038% and 0.205% respectively. Okay, chaps, knowing that, what's the best blend of these isotopes to make the best water standard? Turns out it's called Vienna Standard Mean Ocean Water. And no, I didn't just pull words out of a hat to make that phrase. In 1961, Scripps scientist Harmon Craig created the first standard mean ocean water from various distilled ocean waters and defined its isotopic abundance in comparison to a water standard that NIST had collected from the Potomac River. Ugh. 5 years later, the Vienna-based, hence the name, International Atomic Energy Agency proposed two water standards, VSMOW for ocean-based water and Standard Light Antarctic Precipitation, or, you guessed it, SLAP, for freshwater. This is so damn exciting, I could keep talking about this for hours, but let's suffice to say for the purpose of this video that VSMOW and SLAP were used as the water standards for triple cells to define temperature and calibrate thermometers across the world. One more note, because I couldn't help myself. In 1996, the original sample of VSMOW was running low. To get that perfect blend of isotopes, water was used from Lake Bracciano in Italy, the Sea of Galilee in Israel, and a random water well somewhere in Egypt. Can't make it up. Which brings us to the redefinition of the Kelvin. Rather than experimentally measuring a temperature and basing our degrees off of that, we defined the Boltzmann constant as being exact and based our temperature off of that. Okay, but what's the Boltzmann constant, you say, and how do we find its exact value? Great question, but I have to answer it with another question. What is temperature anyway? We often think of temperature by way of comparison. This is hotter than that, or that is colder than this. But temperature also acts as a surrogate of the total energy of a system. The motion of the atoms in a thing, the motion of the electrons in those atoms, etc., etc. The Boltzmann constant relates total thermodynamic energy to temperature via the following easy equation. E equals Kb, Boltzmann constant, multiplied by temperature. While measuring the total thermodynamic energy of a system is not very easy, measuring the temperature of that system is not typically all that difficult. There's also a relationship between the Boltzmann constant and the molar gas constant, R. This is the same R from PV equals nRT. This equation is R equals Kb times Na. Na here being, you guessed it, Avogadro's constant. Aha! An SI constant that has to be defined by another SI constant. I cry foul. And right you are. As you'll continue to see, these things get messy sometimes with constants looping back on other constants. We'll get to the mole next, I promise, but for now, just trust me that the scientific community is able to measure Na with much smaller uncertainties than it can R or Kb, meaning the measured value of Na doesn't really affect the uncertainty in the measured value of Kb. Okay? At any rate, if you know Na very accurately, you can also very accurately get Kb if you know R. Enter acoustic gas thermometry. If you fill a sphere of a known volume with a known amount of a known gas of known composition at a known temperature, then you can pass acoustic waves through that gas and measure the speed of sound. And using this relationship, here, c squared equals 5RT over 3m. C is the speed of sound, not the speed of light. R molar gas constant, T temperature, and M molar mass of the gas in the sphere. You can then calculate R, which you can then use to calculate Kb via this equation here. Again, all you need to do is measure the speed of sound in a gas of known molar composition at a known temperature to get R, the molar gas constant. From there, you can calculate Kb, given you have an accurate Avogadro constant, and Kb can be used to define your temperature unit. First, the gas. You need it very pure, and ideally you need it to be relatively simple as well. Helium works great for both of these purposes. Being essentially monoisotopic with just a skosh of helium-3 that can be quantified by mass spec, very simple atomically and very inert electronically, helium-4 works great as the gas through which to measure the speed of sound. Next, you need an ideal container. In a perfect world, this would be a sphere, but because we can't machine a perfect sphere yet, the best way is to machine a perfect almost sphere and use correction factors to account for the non-sphericity of the thing. At that point, you fill your almost perfect sphere with your almost perfectly pure gas and pass a bunch of acoustic waves through it, measuring the frequency. Your speed of sound is related to the frequency via this equation, C equals 2 pi alpha, alpha being the equivalent radius of the sphere in which you're putting the helium, nu is obviously the frequency, and Z is your eigenvalue of the acoustic mode considered. No, I don't know what that means, I'm not a quantum person. At any rate, we got the speed of sound. We know the atomic mass of the helium in question to a high degree of certainty, and we know the temperature at which we're measuring all this stuff because we're at the triple point of water. With that, we have R, and we can use our well-known Avogadro constant to calculate Kb. This new approach is clearly impractical in almost every circumstance, so triple cells are still used basically in the same way they were before. The new definition of the Kelvin was created in a way that also maintained its concurrence with the legacy value within current experimental error. In summary, we used to use the triple point of water to define our temperature unit. But the problems of finding a perfect reference standard for that water led to us redefining it based on the Boltzmann constant, a value that relates energy and temperature and can be measured to a high degree of accuracy. And we measure the Boltzmann constant via acoustic gas thermometry and its relationship to the ideal gas constant, which itself has a relationship that can be measured via the speed of sound in a gas. In practice, nothing really changed and the triple point of water is still used as our temperature calibrant, but because we tied the definition to the Boltzmann constant and the laws of nature, everybody now sleeps better at night. And that's nice, right? I have a confession to make. The mole almost broke me. This series is by far the most pedantic thing I've done for the channel. I spent hours reading NIST's dedicated website to the 2019 redefinition of the SI units, and it's been both academically enriching and genuinely interesting for me. And yet, as I read through the dry-as-a-bone descriptions on this one, I almost couldn't finish it. Just listen to this line from BIPM's History of the Mole. The quantity used by chemists to specify the amount of chemical elements or compounds is called, quote, amount of substance, end quote. Full disclosure, there is no exciting way to do this one. There's no fancy block of metal from the 1890s, and the chemistry and physics really aren't all that interesting. For the sake of completeness, though, and because I love you, let's hit the highlights. In 1811, Italian scientist Amedeo Avogadro postulates that the same volume of two gases at the same temperature and same pressure would hold the same number of elementary particles. While Dalton's theory of the atom had been proposed by that point, it wasn't widely accepted, so the term atom wasn't in common parlance of the time just yet. And that's about all Avogadro did. He didn't actually measure the amount of stuff for the constant that bears his name, so his contribution's mainly from the theoretical. Avogadro's number as an expression comes from the work of Jean Pitre, who experimentally determined that value for the first time and was awarded the Nobel Prize of Physics in 1926, at least in part because of that work. Here's the key, so listen up. Chemists figured out that a given isotope of a given element would always have the same number of protons and neutrons. Also, a given molecule would always have the same proportion of the elements of which it was composed. By way of example, the oxygen-16 atom will always have 8 protons and 8 neutrons, or else it isn't oxygen-16. And a molecule of water will always have 2 atoms of hydrogen and 1 atom of oxygen, or else it isn't water. The key is that there is a direct correlation between these atomic and molecular weights, or masses, and weights and masses we could measure at the macro scale, meaning that the same number of atoms or molecules will always weigh the same, and vice versa. A given amount of mass of a given element or molecule will always have the same number of them. This is essentially exactly what Avogadro was saying a century before, but we now had experimental proof of it. The trick now would be defining what that exact value was and where to anchor it. There was minor disagreement across the community, but in 1960, IUPAC and IUPAP physics laid down the law and defined that the isotope carbon-12 would have an exact mass of 12 grams per mole. As you can see, this means Avogadro's number would be based on the mass unit, much more on that in a bit, and would be determined by the number of atoms in 12 grams of carbon-12. This value, as I'm sure many of you know, turned out to be 6.022 times 10 to the 23rd atoms, and this, my friends, is Avogadro's number. Fast forward to the 2000s, and that C12 definition was failing somewhat with how good we were at measuring the exact amount of stuff in stuff. We were so good, in fact, that sometimes we could literally count the number of atoms in something. How was all this possible? Well, it turns out the math is pretty darn easy. In an ideal world, a perfect monocrystal of a monoisotopic element, meaning one single isotope, with an accurately measurable volume would yield the number of atoms in that sample via this. N equals 8V over alpha naught cubed, where N is the number of atoms, V is the volume, and alpha naught is the lattice parameter. With the total number of atoms in the sample measured, we now need the molar mass of the elements in that measurable volume and the total mass of that monocrystal. With that, we can get Avogadro's constant via this equation, m over n, m here being the mass, which then gives us the mass of an atom in our sample. Substituting n from our equation over here and assuming that all the atoms in our monocrystal are pure silicon, we can get the mass of a single silicon atom as the mass of the crystal multiplied by the lattice parameter cubed over 8 times the volume. From there, we use these two relationships. The number of moles equals the mass of the atoms divided by the molar mass of the element, and Avogadro's number equals the number of atoms divided by the number of moles. Combine all these, reduce it down, and you get this equation here. Avogadro's constant equals 8 times the molar mass divided by the density multiplied by the lattice parameter cubed. With this, if you know the molar mass of your elements in your sample, the density of your sample, and by way of the density, the mass and the volume of the sample, and the lattice parameter, that is to say, where each of those elements is in relation to the other ones volumetrically, you can empirically measure Avogadro's constant and prove its theoretical validity. Okay, so which element is best? It needs to be crystalline with a workable allotrope, so not like diamond, for instance. Easy to manufacture, sure, preferably cheap, that'd be nice. Workable across the globe for 2 reasons here. The element needs to be stable in hot climates and cold climates, humid climates and dry climates, and from a manufacturing/machinery standpoint. It doesn't help us if there's like one lathe in Hungary that can make a sphere out of this stuff. Not toxic and not harmful. We have humans touching the stuff, so ease of handling is a consideration. And finally, resistance to oxidation, corrosion, and reaction for sort of obvious reasons. As it turns out, our best elemental option is, as I spoiled a little bit ago, silicon. It's the second most abundant element on Earth after oxygen, so silicon is fairly cheap, and it is not toxic or harmful in its crystalline forms. Finally, and maybe the most important thing about silicon, it's used in the electronics industry, so there is a very robust supply chain, and the technology is very mature, which pretty much checks all the other boxes. Like Moana's first attempt past the reef, not too bad. Except for these minor problems. Silicon has 3 stable, naturally occurring isotopes, SI 28, 29, and 30. While it's just a few neutrons here and there, that's enough to throw off our measurements in accurately determining Avogadro's constant. For that reason, we'll need just a single isotope, in this instance SI 28, at better than 4 nines purity. You'll harken back to our atomic bomb videos and talking about isotopic enrichment, and remember that it is not trivial at all, and 4 nines is some serious silicon enrichment. Next, even if we do enrich our silicon to 4 nines purity, there's other elemental contamination in here. Namely, carbon in our silicon will mess up the mass and density properties of our sphere, and those little carbon atoms will get in the silicon's unit cell, so it wrecks our lattice parameter. Finally, you take your wonderfully monoisotopic silicon with no other elemental contamination and grow a perfect single crystal of it. Then you have to machine that into a perfect sphere, so its volume is exact, and then you have to measure the lattice parameter and the mass. But if you do all that, then, and only then, you can measure and determine your Avogadro constant. Okay, so how'd it work? Well, in a 2-decade effort of labs across the planet, the International Avogadro Project manufactured 2 ludicrously smooth, ludicrously pure spheres of silicon-28. And here's that process to get your perfect monocrystal of silicon-28. First, you take naturally occurring silicon and react it with fluorine, remembering that fluorine is naturally monoisotopic, so it doesn't introduce any other isotopic contamination, and you get naturally occurring silicon tetrafluoride. Next, you enrich your naturally occurring silicon tetrafluoride into greater than 99.999% pure silicon-28 tetrafluoride via gas centrifugation. You take your silicon tetrafluoride here, put it in a big rotating cylinder, and centrifugal force pulls the heavier isotopes, silicon-29 and 30 tetrafluoride, to the outside, and your lighter isotope, the silicon-28 tetrafluoride, goes to the middle. Take that middle material as the feedstock in a successive cylinder, do it again and again and again and again, and eventually you reach your desired isotopic enrichment. It's honestly not that different from how uranium was enriched during the Manhattan Project. Centrifugal separation existed as a technology at the time and was even looked at through the 1940s, but it just wasn't technologically viable at the time to, win World War II. Next, our enriched silicon tetrafluoride is reacted with hydrogen in the presence of calcium hydride to create enriched silane and calcium fluoride. And let's just tip our caps on this one, because aside from the cal fluoride, everything here is dangerous. This is probably wicked corrosive, metal hydrides are water reactive and yield hydrogen gas when they do, and this one is outright pyrophoric. Almost done. Next, the enriched silane was separated from the hydrogen gas, always fun, by being chemically vapor deposited onto an 800 degrees Celsius rod of highly enriched silicon-28 that was 1 centimeter in diameter and about 90 centimeters long. At the rate of deposition, scientists could get 3 kilos a week of highly enriched polycrystalline silicon-28. Finally, the polycrystalline silicon-28 is converted to monocrystalline silicon-28, aka a big-ass single crystal of silicon, via a technique called the float zone. A seed crystal is placed at the bottom of that big rod of polycrystalline silicon-28, and it is electromagnetically heated to its melting point. There, a layer of melted silicon floats, float zone, slowly up the rod, reorienting everything from polycrystalline to monocrystalline, and that's how you get a big ol' single crystal of highly enriched silicon-28. The molar mass of the silicon present was determined by virtual element isotope dilution mass spectrometry, or VEIDMS. Instead of directly measuring the isotopic composition of silicon-28, 29, and 30, the instrument took a known amount of one of those isotopes and doped it into the instrument, thus measuring the ratio change of before and after. It's sort of like a back titration. When you can back calculate the ratio change from doped to undoped, you get an extremely accurate composition of what the isotopes were initially. Other non-silicon impurities were measured by cryo-IR, which, as the name suggests, is regular infrared spectroscopy but done at a really low temperature. Now you've got yourself 6 kilos of the finest silicon ever made. Machine and polish that puppy into a perfect sphere and you can determine Avogadro's number. None of the papers I read went into how the machining and polishing occurred, but if you expanded that silicon sphere to the size of the Earth, the difference between the Challenger Deep and the Marianas Trench and Mount Everest, currently on our globe about 12 miles, on the silicon spheres would in fact be about 10 feet. So these things are smooth. Given the sphere is as idealized a case as we get, you simply measure the mass and the volume of the sphere, determine the lattice parameter of the silicon atoms in the sphere, make sure you account for any impurities in the molar mass and any lack of perfect sphericity in the volume, and then you just apply the algebra from before and you can calculate Avogadro's constant. It turns out there's another way to do this without having to count atoms. It's called a Kibble balance and it measures mass without measuring mass. We'll get into that way more when we talk about the kilogram, but here's the summary of Avogadro's constant. Rather than defining that constant by the amount of atoms in 12 grams of carbon-12 isotope, we in fact just experimentally proved it. We basically made a perfect sphere of silicon and counted the number of atoms per mole. The last entrant on our list is the granddaddy of them all, our mass unit, the kilogram. Historically, mass has always been defined as a given volume of liquid. For instance, the precursor to our friend the kilogram was called the grav and was defined as the mass of 1 liter of water. Formalized in 1793, the OG grav was determined at 0 degrees C, so really it was more like a liter of ice, and its exact mass was determined by none other than Antoine Lavoisier. As we just saw in our discussion of temperature, water as a reference standard can be a bit tricky. People in that era were already figuring that out, so a physical artifact grav was made from metal instead of water. In 1795, the gram became the official unit, and the grav was now called the kilogram. By 1799, the kilogram was defined as the mass of 1 liter of water at 4 degrees C, where that material is maximally dense. The literal physical artifact kilogram was made from platinum, stored at the National Archives in Paris, and remained the mass standard for 90 years. It was replaced in 1889 with the International Prototype of the Kilogram, or IPK, or Le Grand K. This machined right circular cylinder of 39mm diameter and height was made from 90% platinum and 10% iridium. As we discussed on our prototype of the meter, the iridium increased the alloy's hardness but maintained a lot of platinum's otherwise excellent and desirable properties, including great oxidation resistance, high density so the artifact didn't have to be that big, and good electrical, thermal, and magnetic properties. The IPK and 6 sister copies were made to aid in calibration and are stored in the Fort Knox of International Unit Standards just outside of Paris. The monetary value of the IPK is hard to quantify, but it's special enough that it only came out of its triple bell jar configuration 3 times in over 100 years to calibrate other international standards. The US has 5 now obsolete copies of the kilogram at NIST in Gaithersburg, Maryland, for what it's worth. While the IPK itself had no error, remember it's literally defined as the kilogram, other national Czech standards and prototypes have shown slight variations across 130 years of use. We're talking tens of micrograms here, but when it's the thing that mass is literally measured against, it's important. Surface absorption of schmutz was the main reason why these things gained mass over the years, and BIPM developed a method to clean the things. Firm rubbing with a chamois soaked in 50-50 ether ethanol was first, followed by blasting the thing with steam from bi-distilled water. Through all these measurements and verifications and calibrations, the IPK demonstrably lost about 50 micrograms compared to other kilogram standards. There's no plausible reason for why this happened, and some physicists dedicated their entire careers to the kilogram. Really kind of puts in perspective some of my life choices. And this went on until 2019. Let me repeat that. Until 2019, the internationally accepted definition of mass was a block of metal in a safe outside Paris that lost a measurable amount of its own mass. But, my friends, I am here to tell you that is where the scientific community drew the line. The kilogram would no longer be defined by a physical thing. Rather, it would be defined by the frequency emitted by a specific isotope of cesium, the speed of light, and Planck's constant. Wait, how is that any better? Well, it is less intuitive, but it is more accurate and doesn't depend on our ability to accurately measure stuff. Check this. Einstein's theory of relativity says E equals mc squared. E energy, m mass, c speed of light. Planck correlated the same quantity, energy, via h, Planck's constant, nu in this case being frequency. Combine these two equations and isolate mass algebraically to get m equals h nu over c squared. Put all these variables and constants together to cancel out and equal 1 kilogram, and you get this. 1 kilogram equals 1.4755214 times 10 to the 40 those. Well, that makes no sense whatsoever. And that's because mass is being represented here by energy, which is unusual but true. Think about the theory of relativity or atom bombs. The reason why they're so destructive is they literally convert mass into pure energy. So what even is a kilogram? I like this explanation I found online. A kilogram is the difference in energy of a bunch of cesium atoms, you'll note the frequency here is from our cesium atom in the definition of a second, at an excited state compared to that same amount of cesium atoms at a ground state. A kilogram is literally the difference in energy between a certain amount of atoms at an excited state and a ground state. That is a kilogram. Dude. This is trippy. I know, isn't it great? Just to circle back on our units, we've already seen how that hyperfine transition emission from cesium-133 defines time, so that frequency is what gives us our time and speed of light here. The Planck constant was then defined to be exact. How do we know the true value of a defined exact Planck constant, you ask? Well, great question, and the answer is a Kibble balance. At its simplest, a balance is literally that. It's a thing that balances an unknown quantity of thing with a known quantity of thing. When those things are equaled, or balanced, then you know the unknown quantity is the same as the known quantity. The Kibble balance, originally called a Watt balance and named for its inventor, British physicist Brian Kibble, does just that. The elegance of the Kibble balance is that instead of measuring two gravitational forces, masses or weights, what we usually think about, the Kibble balance instead balances a gravitational force with an electromagnetic force. Let's check out the, frankly, really cool algebra on that. Basic math and physics classes will give you this fundamental relationship. F equals ma. F force, m mass, a acceleration. For weight measurements, that acceleration is going to be the acceleration of gravity, so you get F equals mg. This is known as the gravitational force and is one of the at-a-distance forces. At a distance meaning gravity doesn't need to be in physical contact with the object on which it's applying that force. The other two big ones are electric force and magnetic force, which can be combined into this equation here, F equals BLI. B is the strength of a magnetic field operating on a conductive wire of length L with current I. You can combine these two equations here to get mg equals BLI. This way you can correlate gravitational force with electromagnetic force using these two equations. Your standard old-school balance with the little slidey weight thingies balanced two gravitational forces. The beauty of the Kibble balance is it can use an electromagnetic force to balance the gravitational force, instead of using a second gravitational force. In practice, measuring the strength of the magnetic field B to the accuracy necessary for defining Planck's constant was really hard, so Kibble bypassed it via Faraday's law of induction. I've said it before and I will say it again, I am not an electrochemist. My layperson reading of this law is that an electromotive force, force being the key word here, is created when magnetic flux changes. And magnetic flux can change by moving the physical position of an object within a magnetic field. By moving that same length of conductive wire L through our magnetic field B at a given velocity, and thus changing the position and changing our magnetic flux, you can get this relationship. V, big V, voltage equals BL, little v. By substituting BL here back into this equation, you can get mg equals big VI over little v, or mg little v equals big VI, or M equals big VI over G little v. And this is your winning equation and what the Kibble balance uses. In order to measure a very accurate mass, you gotta find voltage, current, gravity, usually a constant, but can be measured by a separate instrument called a gravimeter, and velocity. To do this, a Kibble balance operates in two different modes, weighing mode and moving mode. Weighing mode gets you current, and moving mode gets you the other two, voltage and velocity. And here's your Kibble balance. There's the wheel to do your balancing of the two things, but it turns out in this configuration, both things to be balanced are on the same side. You've got your magnet creating your magnetic field of strength B and your length of conductive wire L. That wire is physically connected to a pan that carries your mass M, and that's about it. I'm purposefully not showing the detectors, both for simplicity's sake and because they're beyond the scope of the video, but suffice to say that in this configuration, we can directly or indirectly measure voltage, current, and velocity. Gravity, again, is measured offline using a gravimeter. In weighing mode, the mass is placed on the pan and the current of the coil is increased until that upward electromagnetic force perfectly balances the downward gravitational force, mg, of the mass in the pan. And with that, voila, you get current. In moving mode, the mass on the pan is removed and the current to the coil is shut off. Then the coil is moved through the magnetic field at a very well-known velocity and the voltage is measured. With that, you get voltage and velocity, and you don't need to know the strength of your magnetic field, remembering back because we algebraically canceled out B and L by knowing big V and little v. Okay, so that's how we get mass? Well, yes, now, but previous to the 2019 SI redefinition, the Kibble balance was used more to measure the Planck constant. If it's a constant, why'd we have to measure it? Exactly! And this was the exact point of the SI redefinitions. At some point you just have to lay down the law and say, this is the thing that we're going to define our unit by. It is exact, it is unmoving, it has no error, it has no uncertainty. The choice for scientists, and the kilogram, and really all the units, but specifically for the kilogram here, would you rather have your mass unit defined by a chunk of metal in France somewhere, or would you rather measure the Planck constant to as accurate certainty as you possibly can get, and then define it as being exact? Well, the scientific community obviously went for the latter. Okay, fine. So how does one measure the Planck constant with a Kibble balance? Super glad you asked. Quick detour. In 1962, a 22-year-old grad student at Cambridge named Brian Josephson proposed a theory in which two superconducting materials would be brought into weak contact of each other and a potential applied across them. Josephson theorized that in this configuration a supercurrent would be created, and it would oscillate at a frequency via the equation nu equals 2eV over h. Nu here is frequency, E is the elementary charge, V is the voltage or potential, and h is Planck's constant. This theoretical relationship was experimentally proven less than a year later, and Josephson was awarded the Nobel Prize for Physics in 1973 for this work. As you can see, this equation allows us to relate voltage and frequency, which is important step number one in determining our Planck constant. For what it's worth, the variable 2e over h was named the Josephson constant for obvious reasons. Josephson is a fascinating dude. Can you imagine doing Nobel Prize winning work at 22? Not even Taylor Swift is that good. When I was 22, I was doing graduate level chemistry work, like classes, not theorizing groundbreaking new concepts. Shortly after his Nobel Prize win, Josephson became interested in, how we say, some less than scientifically rigorous ideas and became something of a pariah in the physics community for it. Do check out his Wikipedia page if you're interested in going all the way down that particular rabbit hole. Alright, that's part one. Part two takes us to Klaus von Klitzing. Von Klitzing discovered the quantum Hall effect, which deals with quantized resistances in two-dimensional electron structures at low temperatures. I don't have any idea either, but suffice to say it allows us to create a relationship between frequency and resistance the same way the Josephson equation allows us to relate frequency with voltage. This leads us to the relationship R equals h over e squared nu. Nu velocity, h Planck constant, e elementary charge, and R resistance. Taking this back to our Kibble balance, remember that it was first called a watt balance. A watt is a unit of power, and power can be defined as a force multiplied by a velocity. Looking at our downward gravitational force, you could make an equation that says P power equals mg little v, v here meaning velocity. Hey, that looks mighty similar to m equals vi over gv, the equation we've been using for the Kibble balance the whole time. Do one piece of algebra, moving these variables from the denominator into the numerator, and you get vi equals mg little v. Now we can correlate the multiplied product of our voltage and our current into a power. Now things start to get really powerful. Pun half intended. We've got our power equation, P equals VI. We've got Ohm's law, V equals IR. We've got the Josephson effect and the von Klitzing effect. Put all these together in a power equation and you get VVR over R. Expand that out and you get C, a constant based on the number of junctions in a known Josephson standard, nu1 and nu2, two frequencies, your Josephson and your von Klitzing constants that can then condense down algebraically into C, nu1, nu2 over 4H. Now we can see exactly how a Kibble balance can measure what the Planck constant is. You'll note here that the elementary charge cancels out algebraically as a variable, so who even cares if that number is accurate? And here are our power equations. P equals C nu1 nu2 over 4H and P equals mgv. Remember, downward gravitational force multiplied by velocity. To get H, Planck's constant all by itself, you've got mgv on the one side, and then you have to move all this to the other side. Basically just take the reciprocal, 4 over C nu1 nu2. And this, my friends, is how a Kibble balance was able to accurately measure Planck's constant. You take a mass of extremely well-known accuracy, measure gravity with your gravimeter, measure velocity via that uncharged coil that went through the magnetic field using Faraday's law of induction. 4 is 4, C is a constant, nu1 and nu2 are the microwave frequencies we use to create the Josephson effect. And this is how we figured out that Planck's constant is what we thought Planck's constant was. With that, BIPM set the value to a defined exact number, and we did basically everything in reverse on the Kibble balance to figure out what mass was and define the kilogram. Woo! Here's the trick though. The Josephson and von Klitzing constants have the Planck constant in them. It's like using the word in the definition of the damn word. Who's to say that Josephson and von Klitzing constants are any good? I searched the internet for multiple hours trying to find this thing, and it turns out it's buried in the mise en pratique, French for how do you get it in practice, of the BIPM document for the unit ampere. Here's how BIPM itself explains it. First for the Josephson constant, then for the von Klitzing constant. Quote, "This value follows from the assumption of the accuracy of the equation Kj equals 2e divided by h, which is strongly supported by a large body of experimental and theoretical works, and the values of blah 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 whatever." Next one, "This value follows from the assumption of the accuracy of the equation Rk equals h divided by e squared, which is strongly supported by a large body of experimental and theoretical works, and the value da da da." End quote. They use the same wording for each of the constants. My read of this is they basically say, while experimentally these values are practically bulletproof, you're just gonna have to take our word for it. So, in summary, the constants used to measure and define the Planck constant have the Planck constant in their own definitions. It all ends up working, so it's a bit semantical, but I'm still pretty surprised that for something this critical, the scientific community couldn't really find a different way. Ultimately, this whole kilogram boondoggle is about how you use the Kibble balance to accurately measure the Planck constant. By equating mechanical force to electric force and using a bunch of equivalencies and pretty damn accurate electric constants from 1990, you can measure velocity, frequency, voltage, and resistance while using an assumed exact mass in order to measure the Planck constant, which you can then use to define the kilogram. Goodness, my brain hurts. Those of you observant enough, and frankly still awake by now, will note that I haven't mentioned the elementary charge and the luminous efficacy of monochromatic radiation and their corresponding units, the ampere and the candela, respectively. And here's the thing, I'm just not going to talk about them. I've already told you electrochemistry is black magic to me, and light intensity doesn't really interest me. Also, I'm just done with this topic. I have spent way too long reading and thinking and crunching variables algebraically in these videos, and I am just not going to do it anymore. Congratulations, you've made it to the end. To summarize, in 2019, most of the SI units were changed from their previous values. Rather than using random assignments or physical objects, they went to being based on fundamental constants of nature, themselves based on physics of the natural world. While groundbreaking in its accuracy and application, the practical effects for those of us not dialed into measuring things with part per billion accuracy was completely negligible. Nothing changed. Numbers on a balance were still the same, temperature felt just as hot or cold as it did before, and that bike ride you went on felt just as long as yesterday. But hey, you did get an extremely long YouTube video of some of the driest and most ridiculous subject matter of all time. So there's that. See y'all next time. You've never heard of the Millennium Falcon? It's the ship that made the Kessel Run in less than 12 parsecs.